provided by the compiler. So if you design a class and you don't provide a copy constructor, you get a default one from the compiler, and that basically will just do bitwise copies and shallow copies on your behalf whenever you do variable initialization. In addition to that, it'll also be used when temporary objects are created. For example, when you pass an object by value to a function or a function returns an object. Similarly, the default copy assignment operator provided by the compiler also does more or less the same thing. Now, in addition to default functionality, obviously, if someone specifically implements an operator of one of these types and specifically does shallow copying at some level, then they have the likelihood where they're going to have these problems as well. Self-assignment is another thing that a lot of C++ books will talk about. Basically, when you're implementing, an assignment operator, you need to check that you're not assigning the same object to itself. Although that might seem silly because, you don't usually have code that have x equals x. Due to pointer aliasing and, indexes into arrays and stuff like that, this can happen from time to time. So failure to check for self-assignment can basically invalidate the object to some extent depending on what you do. If you think about how typically you'd implement operator equals, you usually free the destination's member variables if they already exist, and then duplicate ones from the source or the right-hand side. So if the right-hand side and the left-hand side are the same object, then basically you're deleting member variables and then copying them back into the object. So you're accessing stale memory that you've just freed, and this can lead to a variety of situations depending exactly on what your thing does, but possibly out of bounds memory access, corruption, deleting free memory, etc. Other functions can also be affected as well, like if you have any other member function that takes an object of the same type and you accidentally pass an object to itself or something like that. And also maybe other operators such as operator plus equals might be interesting. We've got a real simple example of that here. We've got like this example ACL list class, and this is kind of intended to protect some sort of resource that it's pointing to, and you can see you've got a vector of individual ACL entries. So because this particular function fails to check for self-assignment, you can see they allocate a new resource based on the existing one, and that's fine. And then they clear their ACLs vector, and they go ahead and copy the one from the right-hand side. But because they've actually, if in the case of self-assignment, they've cleared the one from the right-hand side and the left-hand side. So essentially they'll lose their entire ACL list in that situation. The third thing is state inconsistencies. Now, everything we've talked about up to this point is really state inconsistencies, but in this particular context, we're sort of talking about member functions, regular member functions of an object that you implement. So usually you need the object to be consistent at all times, which basically means that all the member variables have to be synchronized with each other to some extent. If a member function can fail, you have to check whether the object is going to be rendered into an inconsistent state of some type. And to do that, usually you need to determine what happens. Is an exception thrown, is an error returned, or what? Now, errors can be pretty easily ignored, and you'll usually want to consider the implications of that. Exceptions can also be ignored, but it requires the developer to explicitly, catch it and not do what he's supposed to do. So that's kind of less likely. The same applies for constructors as well, which are kind of interesting in that they don't return values typically. So usually the only option the developer has there is to throw an exception. Otherwise, you end up in with an object that's potentially not completely initialized. So if you have some sort of object that fails to maintain consistency, particularly in these erroneous situations, then you have the potential for some sort of vulnerability if you attempt to manipulate that object, call a member function or whatever at some later point in time. And this is especially true for destruction because usually if you signal an error, especially through an exception or something, and it triggers an automatic stack unwind or something, and the object is on the stack, then that object is going to be automatically destructed, and that could be potentially dangerous. So we've got an example here of how that can happen. You can see we've got a constructor for a fictitious board game, and it basically dimensions the board and then allocates a grid based on that. The constructor uses calloc, which is actually C and not C++. But in reality, C and C++ are mixed all the time, so you'll get over it. But basically, they neglect to check that calloc actually returns successfully, and that basically creates an inconsistency in the object, in that mx and my basically imply that the m squares member variable has been allocated when in fact it hasn't been allocated successfully. So if at some point later on you call the set square function down below there, you'll see that they reference m squares at some sort of offset, and if that offset adds up to be, a valid page it can be written to, then you might have some sort of memory corruption problem there.
So we can dig into the effects of these root causes as well and talk about how this could lead to security issues. And this is one of the things that I find the most when I talk to people who are just developers and not security people, is that they'll know that a program crashes and they'll assume that they need to fix it, of course, but they won't talk about exactly what the implications of that and how bad it could possibly be. So stale pointers, and everything we talk about is really the result of inconsistent state within this section here. You have a pointer to either memory that's no longer in use or it's been used twice in some place. And we'll dive into some specialties of this here, but what really is actually beneficial to an attacker with C++ is that there's all this machinery on top of the core allocation and deallocation of memory. So the use of vtables to destroy objects, for example, can be very interesting. And the vtables are less protected than traditional control flow transfer storage, such as return addresses or function pointers. You'll quite often see those protected by stack cookies or XOR encoded with some random value, et cetera. We have yet to see that be done for vtables. So they're again much more wide open. So if you have a heap full of objects, you have a much better chance of exploiting a memory corruption condition in that case, rather than a heap that's full of just regular blocks of memory. So to dig a little bit deeper, if you have member functions called through an arbitrary object pointer, or if you have a member function that's called with this pointer that's invalid, you can get execution at an arbitrary address by dereferencing the vtable pointer possibly, or type confusion, where you have the mixing of what used to be an integer possibly, but now is interpreted as a pointer. It can lead to modification of memory. It can be very application specific, but our experience has been that when we find these bugs, they are very reliably exploitable in a lot of cases. And this is because of this C++ machinery on top of the the core OS allocator. So to even specialize a little bit more, one example we'll go into, and we found this one a little bit interesting to show, is the double or uninitialized deletion of an object. So when you destroy an object twice, for example, you get more than you get with, as an attacker, you get more than you would get with a double free in C, which is becoming increasingly hard to exploit with some of the heap implementations out there. And so what happens is you have the operation of actually deleting the object in addition to actually freeing the memory. And that will operate on memory that's out of bounds. So we'll show here a diagram here of what was an object before destruction with a few virtual member functions. We found that the virtual member functions tend to be ordered by the way or the order you declare them within the actual within the actual source code. That's the way the compiler orders them in the vtable. So once this object gets destroyed, it gets passed to the operating system free function, which will then free up the block. On Windows here, you'll have a doubly linked list, next and previous for heap chunks. And so, in the situation where an attacker has some control over what type of data is freed, the next heap chunk on that free list could likely be attacker-controlled data. That'll be dereferenced if you delete the object twice as the vtable pointer. You call the destructor, which is then user data. It's the third element within that vtable. So that hopefully that coloration, that overlay is clear. But it's a fairly basic concept, fairly reliable to exploit. As you can see, the security consequences of it are potentially pretty serious.
Okay, so now we're going to kind of talk about some of the security implications of the standard template library, or the subset of the standard C++ library. that's the standard template library. So real quick introduction if you're not familiar with it. There's three key components to it. There's containers, which are abstract data structures that you use to manage collections of objects. So like in C, where you'd have to write your own linked list or binary tree, the STL is going to provide you some data structure that will handle all the details for you. And we'll talk about some of the different containers later on. Another key concept is iterators, which is the preferred idiom at which you access the elements in containers. So you can use the iterators. They're kind of like pointers with magic extra bits. So you can use the iterators to walk through the elements in a container and get access to the elements. And the third key component is algorithms, which are intended to be independent from the containers, basically, and they process across containers, although there's lots of dependencies. But so you have stuff like search, sort, swap, et cetera. And one worth pointing out, standard copy is kind of like the idiomatic C++ mem copy. And sometimes, depending on template specialization, it'll actually end up being a mem move or a mem copy, which, of course, is interesting. So there's a variety of STL implementations, and the security of the implementations varies pretty widely. The very latest Microsoft, with all the secure stuff, is quite strong and impervious to much of what we're going to discuss here. But versions prior to that and glibc implementations tend to kind of track the spec as far as the security checks they have. So this discussion should apply to most other STLs, STL port and the SGI one. So there's four kind of vulnerability classes that we wanted to isolate, and these aren't groundbreaking by any means, but these are the kinds of things that we need to, as we're auditing C++ code, we need to keep an eye out for. So the first one is implementation problems in the STLs themselves. The second is problems with invalidation. The third is problems with ranges, logic problems with ranges, and the fourth is simple problems with boundary checking. So we'll start with the first one. By STL implementation vulnerabilities, basically what we mean is low-level vulnerabilities in the STL itself, like integer overflows. If you try to, insert a whole bunch of stuff, what happens? So the current latest versions of both G++ and Microsoft are generally resilient to this kind of thing, which is kind of surprising considering some of the other checks that they don't have. But they generally will fail gracefully or fail quickly. They won't leave you in a state where you think you have more memory than you do. So obviously STL versions change over time, and determining the STL version is kind of tricky because it's template code, so it depends on what it was compiled with. So basically, you just kind of got to get your hands dirty if you're in a binary and kind of compare it to what you know the existing STL. You can use kind of auxiliary indicators to guess the age of the overall technology. So here's an example of how Microsoft fixed. This is an internal allocator I think used in the vector class, and you can see that they take a pointer div t type n, which is the number of elements, and then a type, which they use to grab the size of the type. So you have number of elements times size of the element. So that's pretty straightforward multiplication overflow situation. Now you can see how they fixed it. First of all, it's a size t instead of a pointer div, so it's unsigned. But more interestingly is you can see there is the idiom for preventing a multiplication overflow. So, and it'll actually throw a standard bad alloc exception there. So we got to move quick.